let's take a look at a past exam too. I'm pretty sure this one is from fall of last year because that was the last time that we had on-campus class. So this will differ from the one that you're going to get this semester because the one you get this semester will be like exam one, that'll be done in mastering engineering, and it will come from a pool of questions from both chapters 5 and chapter 6. So you're going to get 5 questions, as mentioned. Be very similar. So this was the first question that I asked, and you're going to determine the forces in those 4 members, state of their intention or in compression, and include any free body diagrams. One of the problems I have when I'm doing these slide presentations and recording is I can't go backwards, so hopefully you'll either pause the video or come back to this as we go through the solution. So first thing you should probably notice and hopefully notice is, right, method of joints is if you're asked for everything, method of sections is 3 or less. You're being asked for 4 in this case, so this is a hybrid problem. Right? Hybrid problem means you're going to have to do both method of sections and method of joints. Hopefully you recognize by taking a look, right, CD, CJ, and JG. You can cut through those 3. That's where we're going to do method of sections. And then you're going to have to do method of joints either at C or G. G is going to be the one you want to pick because you're going to have less unknowns. Actually, I guess, yeah, you're going to have less unknowns if you pick that one. So that's the one that we will go with. Symmetrical design, however, it's not loaded in a symmetrical manner. So what's on one side is not necessarily what's on the other side. So bear that in mind as we go through the problem. So if you remember the steps for doing this type of problem is find global equilibrium if you need to. You are going to need to because in this particular case, hopefully you recognize that the piece on the right is going to be the simpler side to solve. So we're going to need the reaction at point E, which appears to be a pin in this case. So what did I do first? Well, first, and I was guilty of not actually drawing a free body diagram, but if you start with the whole truss in this particular case, find your support reactions. I did both A and E, right? All we actually need is E. Hopefully you can recognize based upon the way this thing is loaded, there's no X direction reaction, so EX is 0. You'll see that I found Na because right the A side we had looked like a roller and we had a pin, so we had a EY piece on the other side. So you got those values. So then we take and we draw a free body diagram of the easier side. So that, as I mentioned, is the one on the right. You can see I put in the EY value. I just called it E for whatever reason, doesn't really matter. You got the 6 that was on the external load, the 9 that's the external load, and you got these 3 unknowns. The values that are filled in there are the values for the hypotenuse. Well, the hypotenuse is gotten from the other 2 sides. The other 2 sides I took from the original problem. So again, pause the video if you forgot, take a look back, and you'll see where those values come from. So I did this, there's a number of ways you can do the problem. I did this by doing moment equations. So I'm going to find a moment at C, right? Point C will get rid of CD and CJ and will let me solve for GJ, right? Then I did a moment at point E, right? Point E gets rid of all that 6 and that EY value, right? It also will get rid of your GJ because that goes through point E. It'll get rid of your CD because that goes through point E and will allow you to solve for CJ. Then, last but not least, I took a moment at point J, right? And that's going to get rid of CJ and GJ and will let me solve for CD. So, how did I do that? Did my moment at point C. So when I'm solving for my moment at point C, what do I have? I have CD and CJ going out, so I have the X piece of GJ, and right, the Y piece is going to go Oh, the x and the y piece, there we go, right at the end of the equation. I have the 9 is going to contribute, the 6 and the EY are going to contribute, which I've got all those pieces there. Allows me to solve for FGJ. Right? When I move on to E, right, when I'm taking the moment at E, the 6 kilonewton force and the 20.2 for EY fall out, right, as also GJ and CD drop out. So I have both an X and a Y piece for CJ that contributes to a moment at E. And I also have the 9 kilonewton part contributes to a moment at point E. Put those in the equation, I get FCJ. Take a moment at point J, right? In that case, I'm going to get rid of GJ, CJ. I'm going to get rid of the 9, but I still got the 6. I still got the EY component, and I have the FCD component. Put that all in. I can solve for FCD. All right, so now I've got 3 of the 4 pieces, right? I've got FGJ, and I've got CJ and FCD. Right, so if I move to point G, right, the last piece that I need that it was asked for is FCG. If I move to joint G, right, I know FGJ, I don't know CG, that's what I need to solve for. I don't know HG because, again, the truss is symmetrical, but the loading is not, and the 12 kilonewtons is what's externally applied. So I can sum the forces in the x direction. So what do I have in the x direction? I've got a piece of FGJ, and I've got a piece of FHG. Try saying that fast. So those two are going to be equal to each other. All right, so that allows me to solve for FHG. Right, then when I solve for the y direction, everything has a y component. So I'm able to solve what I just got for FHG, plug that in the equation, solve for my last unknown FCG, and I get 7.5 kilonewtons in tension. So you'll see that the first two are compression, you get a negative value, and the third one is in tension, get a positive value. So that was the first problem that I'd asked on that exam. The second problem here, which you might notice, is a frame problem. I kind of cheated on this one, you'll see in a second. So in frame, remember the difference between a frame and a truss is a frame or a machine, you've got a multi-force member. So this ABC piece is a multi-force member, right? BD is a two-force member and can be replaced with a vector, right? Just one reaction force there. So what you have to do for this particular problem is we need to solve for, there's pins at point A and there's pins at point D, and there's a weight of 15 kilonewtons pulling down on it. This is like one of the ones from the textbook, and you'll see how I kind of stole this in a second. So there's kind of two pieces, right? You've got to blow this thing apart. You've got the rope part, so you have to find the tensions in the ropes based upon the weight, and then you need to find for your multi-force member. So these are the two pieces that you're going to do, right? You're starting with the rope. If there's 15 kilonewtons pulling down and there's that rope pulling up, right, it's got to have the same value on each side. So if there's 15 pulling down, there's 7.5 pulling up on both those ropes. Like one rope is tied to the member ABC, the other rope goes back to the wall. So there's 7.5 kilonewtons on that one, 7.5 pulling down on each one of them. Right, AX, AY, and FBD are our unknowns. So we need to solve for those. So first piece of that first line is what we just did to get the tension in those cables. Right, the second part is solving for that ABC piece. Right, so we take a moment at point A, and you'll see we have a piece of the FBD that causes it. We've got the 7.5, the three pieces of the 7.5 all cause a moment at point A. So we plug in the values and we solve and we get FBD of 37.5 kilonewtons. Right? What do we have in the x direction? Well, we've got the AX piece. We've got a piece of that FBD, and we have 17.5, right? The one that's on top pointing in every direction. So that stuff in, we solve for AX, and we sum the forces in the Y direction. What do we have in the Y direction? We've got two 7.5s, those two ropes are pulling down. We've got AY, and we've got a piece of that FBD. Right? We plug in those values and get 15 kilonewtons. So that was the second problem from that exam. So problem 3 is a little bit trickier here. It's a 3D problem. In this 3D problem, I'm flipping through my notes here so I can get back to my page here. So in this 3D problem, right, we've got a square bar that this thing fits loosely into. Right, so the way that this thing is sitting, we need to find the reactions at point A and at point B. Well, point B is essentially a roller or a rocker, right? So there's just going to be a normal force at point B. Right? At point A, the only direction that this thing can move in is the Z direction. Right? So there's going to be a reaction force in the X, there's going to be a reaction force in the Y, there will not be a reaction force in the Z, and there will be moments in all three directions. Why? Because it's square, so we can't turn it around the axis. And we have a component force, right? They took the force at the end of the bar and broke it into the components into an X, Y, and Z piece. So that's kind of nice that they did that in this 3D case. So what do we need to do? Well, first off, we want to draw a free body diagram, which looks like this beautiful drawing that I've drawn right here. And you can see all those pieces that I have put on there, right? We've got the three moment reactions at point A. We've got a reaction in the X direction. We have a reaction in the Y direction. We have a normal force acting at B, and then we got the three forces that are applied. So what we are going to ultimately have to do is we're going to have to solve for all these forces, right? So we're going to have to sum the forces in the X, sum the forces in the Y, sum the forces in the Z, and moment equations are what we can do to solve this particular problem, right? For moments, remember, we need force times distance for moments. So how do we get force? Well, force is given to us, right, Mr. Good guys? How do we get distance in a 3D case, right? We need position vectors. So we're ultimately going to have to find a position vector RAB and an RAC position vector so that we have those two position vectors so that we can multiply those forces by the distance. Remember, cross products, right? And that's what we're going to have to ultimately do. So here's how we did this problem. Here's how I did this problem. Identified points A, B, and C. Right, so I can find my position vector RAB, my position vector RAC. Right, my force at point A is simply going to be the AX and the AY force. I drew them both in the negative direction, so that's why they've got negative signs associated with them. And the force, right, that was given to me in the problem was given to, well, to you also, was given in X, Y, and Z pieces, right? X and Y were positive values and Z was a negative value as shown there, right? And then that normal B force, the normal B force is all in the Z, positive Z direction as we drew in the free body diagram. So I got all the pieces here now, right? So instead of summing the forces in the X, Y, and Z direction individually, what I did was take and solve them all by summing them all at the same time. So we're going to sum the A forces, we're going to sum the F force, and we're going to sum the NB force, right, based upon what we had on the previous slide. So we're going to do that is we're going to combine the X's, the Y's, and the Z's together. Notice we've got the three unknowns, AX, AY, and B. All right, so we solve for each of those unknowns as I've done there. Pretty much falls right out of the equation as long as we set up everything right in the previous slide, which we did. So what do we need? What do we have left? We've got all these moment equations. So we did the same thing. We're going to sum the moments at point A, set them equal to 0. So what do we have for the moments at point A? Well, we got those MA pieces, which you can see I've written down there. We've got the moment caused at point A by NB, and we got the moment caused at point A by the F, the force at the end of the bar there. So we need to do cross products for those. So what do we get? We get our three unknowns, and we get a cross product for RAB cross NB, and a cross product for RAC, our position vector, cross F. Right? We do out all the math, we get that mess, and we're able to solve for our unknowns. Right? So if we take all those pieces, the X piece ends up being 1 kilonewton meters. The Y piece ends up being minus 200 Newton meters, and the Z piece ends up being 1.5 kilonewton meters. Remember, positive sign means counterclockwise, negative sign means clockwise direction. That was problem 3. So problem 4, probably the easiest problem of the bunch, right? This is a chapter 5 problem in this particular case. So you're going to determine the reactions at the supports. So you've got a pin at point B, you've got a rocker at point A. So you've got a normal force at A, you've got an X and a Y component at point B. So you want to determine those things. You got a distributed load. So remember, with distributed loads, we can take and make them essentially point loads. These are both triangles. So 1/2 base times the height is the equivalent value, and it's always a third of the way from the base of the triangle. Now, I took this one from the text and I modified it, and I very nicely took, right, one side is 6, one side is 5. 5's not so easy to divide by 3. So I was kind of nice to you the way I did that. I say that sarcastically. So here's my free body diagram, right? I've got my NA piece on the left side. I've got my BX and my BY piece. Those are our unknowns. I've got the force 1 and the force 2 from those two triangles, the distributed load made into the point loads. I've got directions set out here so that I can do moments for either side, because actually I do a moment equation from B, I do a moment equation from A, and put those together. I have an NAX and an NAY. I broke it into its components just in my drawing so I can kind of keep them straight. Right? When I do my moment at point B, right, NAX is going to go through point B. It's not going to contribute, but the NAY piece will. Right? Same thing when I do my moment at point A. BX goes through point A, doesn't contribute, but BY does. So here's the calculation. So you can see what I've done there is I've done the 1/2 base times height. I've got the two values. On the previous slide, you saw where they put them. So I wrote my moment equation for point B. What do I have contributing for a moment at point B? I've got the NAY piece, right? I've got F1 and I've got F2. Right. The B's fall out because I'm taking the equation at point B. With that, I'm able to solve for NA. So I have the normal force at point A. I wrote another moment equation you could have done some of the forces in the X and the Y direction, but I like to do moment equations. I don't know. So I did a moment equation at point A that knocks out the NA piece, right? Knocks out the BX piece. So all I have is the BY piece, and I have the F1, the F2, right? Those both contribute to the moment. I'm able to solve for BY, right? Last but not least, I sum the forces in the X direction. What do you got in the X direction? You got BX, and you've got the X component of the NA piece. Plug those values in, voila, you've got BX. So there you go. There is an example of exam number 2.